Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight's journey will take us to the darkest corners of the universe, where gravity bends light itself and silence hides the most profound secrets of nature. We'll drift together into the mystery of black holes, those strange, invisible places where time hesitates, matter collapses, and yet somehow the story of everything may begin again. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey together. If your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Imagine the night sky above you, vast and still, dotted with the faint shimmer of ancient light. Somewhere out there, beyond the veil of what you can see, lie the most mysterious objects the universe has ever created. Black holes. They are not monsters waiting to devour, as stories sometimes suggest, but rather the universe's deepest teachers. Each one is a kind of laboratory carved from space and time, where the laws of physics themselves are stretched to their limits. Some physicists even say that within these cosmic abysses, we may find the key to uniting everything we know. The smooth, curving world of Einstein's relativity and the restless, jittering dance of quantum mechanics, the two greatest languages of the universe forever trying to understand each other. You might think of general relativity as the language of the grand, the cosmic, the serene. It describes how stars move, how light bends, how galaxies waltz together across billions of years. Its equations, though complex, speak of elegance and order. But quantum mechanics belongs to the microscopic world, the land of atoms and particles that blink in and out of existence. It is strange, unpredictable, and alive with uncertainty. One deals with curves and continuity, the other with jumps and probabilities. Most of the time, they live peacefully in their own domains. But at the edge of a black hole, these two languages collide. And it is here, at that invisible boundary known as the event horizon, that their disagreement becomes impossible to ignore. If you could drift toward a black hole, you would first see the stars behind you begin to distort, their light bending into rings and arcs. You would be drawn forward, not by any pull you could feel, but by the curvature of space itself guiding you along, the most natural path. The deeper you fall, the slower time appears to pass. From your own point of view, everything feels normal. But to a distant observer, your motion slows, your signals stretch, and your image fades into red until you seem frozen in time, suspended forever at the edge. It's one of the universe's most delicate illusions, each viewpoint true in its own way. Physicists call that invisible boundary the event horizon, the point beyond which even light cannot escape. It isn't a solid surface, but a limit written into the geometry of space-time. Beyond it lies a region where the known laws of physics simply stop working. We can describe what happens just before you cross that threshold, but not what lies beyond it. Einstein's equations predict that everything that falls in continues to collapse without end, shrinking into what's called a singularity. An infinitely dense point where the fabric of space and time themselves cease to exist in any familiar way. But even that phrase, a point in space, might be misleading. Some physicists, like Roger Penrose, suggest that the singularity is not a place at all, but a moment, the end of time itself, a horizon within a horizon, where not only matter but the meaning of before and after dissolves. It sounds frightening, but perhaps it's not destruction, it's transformation. The way a wave disappears not because it has died, but because it has joined the sea. The matter, energy, and information that vanish behind the horizon are not truly gone. They're woven into something we don't yet understand. And that mystery, that tension between what we know and what we cannot see, is what makes black holes so hauntingly beautiful. As we lie here, letting the night stretch above us, it's comforting to realize that these colossal puzzles are not rare. Our galaxy alone is home to millions of black holes, remnants of stars that once burned with unimaginable brilliance, and at its very heart lies a supermassive one, called Sagittarius A star, 4 million times the mass of our Sun. It sits quietly now, feeding only occasionally on drifting clouds of gas, its presence revealed by the dance of nearby stars. In April of 2019, astronomers captured something extraordinary, a photograph of the glowing ring of light surrounding another such giant in a galaxy called M87. That image was humanity's first direct glimpse of an event horizon shadow, the faint outline of space-time folding in on itself. For a moment, our species reached into the heart of darkness and saw a reflection of order, a structure that made sense, the math of Einstein, written not on paper but across the sky itself. And yet, as perfect as that shadow seemed, it whispered another question, a quieter one, almost like an afterthought of the cosmos. If everything we know can be bent, swallowed, or slowed to a halt, what is it that remains? Perhaps that's where our curiosity truly begins. Not with fear, but with wonder, the wonder of knowing that the universe still holds secrets gentle enough to lull us to sleep and deep enough to dream within. If we drift a little deeper into the story, it leads us back in time to the first minds who dared imagine that light itself could be trapped. If we keep walking along this quiet path, the story of black holes begins not with Einstein or modern telescopes, but with a quiet thought in the 18th century, long before anyone had seen a galaxy or imagined the universe as vast as we now know it to be. It begins with two men who spent their nights not gazing through powerful observatories, but sitting by candlelight, scribbling equations with ink that faded as fast as their ideas burned bright. One was an English clergyman named John Michel, the other a French mathematician named Pierre-Simon Laplace. They lived in an age when science still smelled of parchment and patience, when gravity was understood through Newton's lens, as an invisible hand pulling on every object in the cosmos. Michel's idea was simple, almost childlike in its elegance. He asked, what if a star were so massive and its gravity so strong that even light could not escape it? He used a concept we now call escape velocity, the speed needed to break free from a world's pull. Here on Earth, that speed is about 11 kilometers each second, fast enough that only rockets or dreams could manage it. For the Sun, with its much greater mass, that speed rises to roughly 600 kilometers per second. Michel imagined what would happen if a star grew heavier and heavier until the escape velocity reached the speed of light itself. At that moment, he realized, light would fall back upon the star, unable to flee. The object would become invisible, not because it ceased to exist, but because it could no longer send any signal out. He called such an object a dark star. Laplace, working independently, reached the same conclusion. Neither of them had the tools or telescopes to prove it, but their intuition was astonishingly close to what modern physics would one day reveal. In their minds, these dark stars were not monsters but mathematical curiosities, places where light, the swiftest traveller they could imagine, would be trapped by gravity's embrace. It's humbling to think that this seed of imagination sprouted in an era when the word universe meant something far smaller. To Michel and Laplace, stars were like lanterns scattered through a celestial dome, and space was simply the dark canvas between them. Yet even then, the idea of something invisible and powerful, a kind of cosmic silence, was already forming. It would take over a century before anyone truly understood what their thought experiments implied. When Einstein published his theory of general relativity in 1915, the language of gravity changed forever. No longer was it a force pulling from afar. Instead, it became a story of geometry, of space and time bending around matter like fabric around a weight. Imagine the universe as a vast invisible sheet. When you place a star upon it, the sheet curves, and anything nearby, planets, comets, or beams of light, follows that curve. Gravity in this view isn't a hand tugging but a whisper of shape. The heavier the object, the deeper the curve. This shift in understanding meant that Michel's dark stars weren't just possible, they were inevitable. Relativity allowed for the idea that space could curve so steeply that even light's straightest path would loop back on itself. But the equations were unsettling. They seemed to predict not only deep wells of gravity but also strange edges of reality. Horizons where time slowed down, where the familiar rules broke apart. Einstein himself didn't quite believe these mathematical abysses could exist in nature. To him, they were beautiful but unphysical, curiosities in the equations, not in the sky. It was Karl Schwarzschild, a German physicist serving on the front lines of World War I, who first found the exact mathematical description of what we now call a black hole. Working by candlelight in the mud and smoke of the trenches, he solved Einstein's field equations for the simplest possible case: a single, spherical mass in empty space. His solution revealed something astonishing. If a star were to collapse beyond a certain radius, a critical threshold now known as the Schwarzschild radius, its gravity would trap everything, including light. This wasn't science fiction. It was geometry written into the universe itself. The Schwarzschild radius can be expressed with a small, graceful formula: 2 times the gravitational constant times the mass, divided by the square of the speed of light. But rather than focus on numbers, you can think of it as the balance point between existence and disappearance. Every object, from a pebble to a planet, has such a radius, tiny for small things, immense for stars. If the sun were squeezed down to about 3 kilometers across, it would cross that threshold and vanish behind its own horizon. Earth, if compressed to the size of a marble, would do the same. When scientists realized this, they began to see the universe in a new light, or perhaps in new shadows. Black holes were not exotic exceptions. They were natural outcomes of the same physics that made stars shine and galaxies spin. They were the punctuation marks in the cosmic story, periods at the ends of stellar sentences. Still, for much of the 20th century, even as equations whispered of these invisible objects, many physicists doubted they could truly exist. Nature, they thought, would find some elegant way to avoid such extremes. But nature, as it turns out, is not afraid of extremes. The first real evidence came from the stars themselves, from binary systems where one visible star seemed to dance around an unseen partner, moving as if tugged by something massive, yet invisible. Later came X-ray signals, bursts of radiation from matter spiralling into the dark, heating up as it fell. It was as though the universe was sketching the outline of Michel's dream in light instead of ink. Even today, when we picture a black hole, we are seeing not the thing itself, but its absence. The light bent around it, the echo of its gravity painted in photons. And in that sense, black holes are less like voids and more like mirrors, reflecting the limits of our own understanding. They remind us that sometimes, to grasp the full beauty of the universe, we must look not only at what shines, but at what hides. As our quiet exploration drifts onward, the story carries us from the imagination of 18th century thinkers to the strange, graceful mathematics of Einstein and Schwarzschild. Yet the most profound mysteries still lie ahead. If gravity can fold light into silence, what does it do to time itself? What happens at the very edge where motion slows, where even the universe seems to hold its breath? The path now carries us toward a deeper understanding of gravity itself, the quiet force that shapes every motion, every breath, every orbit in the cosmos. You can feel it right now, pressing gently beneath your body, holding you close to the Earth's surface. Yet this same familiar force, so steady and dependable, becomes something extraordinary when seen through the eyes of Albert Einstein. He didn't see gravity as a tug or a pull, but as a graceful distortion in the geometry of reality, a soft curve in the very fabric of space and time. It's a strange phrase, fabric of space-time. It might help to picture it as something tangible, a vast, flexible sheet stretched in every direction. On this sheet you place a heavy ball and the surface dips. Roll a smaller ball nearby and it begins to circle the depression, not because the larger ball is pulling on it, but because the surface itself is curved. This, in essence, is Einstein's vision. Planets orbit stars not because they are yanked by invisible strings, but because they are following the natural contours of the space around them. Before Einstein, Newton's law of gravity had ruled for over 2 centuries. He described gravity as a force that acted instantaneously across empty space, linking every object to every other, no matter how distant. It was a beautiful model, and it worked astonishingly well. But it always contained a quiet unease. How could a force leap through emptiness across light years without anything to carry it? Einstein's insight resolved that mystery by showing that space itself isn't empty. It is a structure, pliable and dynamic. Where there is matter, space curves, and where space curves, matter moves. To Einstein, space and time were not separate entities, but threads woven together. A massive object doesn't simply bend space, it also bends time. The stronger the gravity, the slower time passes. Clocks tick differently depending on where they are. The more massive the object, the deeper the well and the slower the rhythm. You might not notice it here on Earth, but even between your head and your feet, time flows at slightly different speeds. The difference is microscopic but measurable. Einstein's equations predict it perfectly. In the presence of a black hole, that effect becomes breathtaking. Imagine floating far from any planet, where time flows freely and evenly. Now, begin to drift toward a massive object, like a neutron star or a black hole. As you approach, the seconds stretch. Your heartbeat slows, not from fear, but because time itself is being drawn into that curve. To a distant observer watching you fall, your motion appears to slow until, at the edge of the event horizon, it seems to stop altogether. The light from your ship reddens, fading into darkness, as if swallowed by night. Yet from your own perspective, nothing unusual happens. You pass the invisible boundary smoothly, unaware of the great divide you've just crossed. This contradiction lies at the heart of relativity. Both views, the one who watches and the one who falls, are true within their own frames of reference. The universe does not choose one reality over the other. It allows both to exist simultaneously, harmoniously. It is not a trick, but a reminder that truth in physics, like truth in life, often depends on where you stand. Einstein's mathematics captures this balance with an equation so compact and powerful that physicists still speak of it with reverence. Written simply, it says that geometry equals gravity, that the curvature of space-time is directly related to the matter and energy within it. The formula uses a handful of symbols, curvature on one side, energy on the other, but we can whisper its meaning without numbers. Matter tells space how to bend, and space tells matter how to move. When you walk across the floor, you are tracing a tiny path in curved space-time. When the Earth circles the Sun, it is following a curve in the solar fabric, an endless fall around a gentle well. Even light, though weightless, is bound by this curvature. A beam passing near a massive star bends ever so slightly, its path deflected by the gravity of starlight itself. This bending of light was the first major test of Einstein's theory. In 1919, during a total solar eclipse, astronomers measured the apparent positions of stars near the darkened sun. They had shifted just as Einstein had predicted. Overnight, the quiet mathematician from Bern became a global icon. The bending of light is beautiful enough on its own, but in the context of black holes, it becomes something otherworldly. Near such immense gravity, light doesn't merely bend, it can orbit. Photons can circle the black hole like moths around a flame, tracing rings of brightness just outside the event horizon. Beyond that, even light's courage fails, and it spirals inward, never to return. From afar, we see a halo of fire surrounding a circle of perfect darkness. It is not a hole in space, but a place where geometry is folded back upon itself. All of this arises from Einstein's realization that space and time are alive. They can stretch and twist and ripple. Decades after his death, detectors on Earth would feel the faint tremors of those ripples, gravitational waves, sent across the cosmos by colliding black holes. The universe, it turns out, is a musical instrument, and gravity is its sound. The notes are deep, impossibly slow, but they carry the rhythm of creation itself. To think that all of this, the bending of light, the slowing of time, the dance of planets, can be expressed in one quiet idea: geometry as destiny. Einstein once said he wanted to know how God created the world, not the details, but the thoughts themselves. In discovering relativity, he glimpsed one of those thoughts, a whisper of logic so pure that it feels less like invention and more like revelation. So tonight, when you feel the pull of gravity keeping you anchored to your bed, imagine it not as a force dragging you downward, but as a gentle curve guiding you along the surface of the planet's space-time. You're resting in a tiny cradle carved into the universe's great fabric, one that holds the oceans, the mountains, and every quiet sleeper sharing this same cosmic rhythm. And somewhere out there, in the deepest wells of gravity, that same geometry continues its quiet work, folding light, stretching time, and carrying us ever closer to the heart of the mystery. From here, the story opens into a quieter place, a boundary not marked by walls or light, but by the very rhythm of time itself. Imagine approaching the edge of a black hole, where the calm logic of physics begins to tremble like a candle flame in a soft wind. It's called the event horizon, a name that sounds like poetry whispered by the universe. The words mean simply this: a horizon beyond which events can no longer reach us. Nothing, not even light, can cross back once it passes through. But before we step too close, it helps to remember how strange gravity can become. According to Einstein's geometry, the closer you are to a massive object, the more time slows down. Clocks at sea level tick slightly slower than those on a mountain. For most of us, this difference is invisible. It takes precision instruments to even detect it. But near a black hole, this effect becomes breathtaking. The slowing becomes so extreme that to a distant observer, anything falling toward the black hole appears to move slower and slower until finally, it seems frozen at the edge, caught between motion and stillness. Imagine watching a spacecraft fall toward a black hole, its radio signals stretch into longer and longer wavelengths, fading to a deep red before vanishing completely. The ship itself appears to hang motionless at the horizon, its last moment stretched across eternity. Yet for the astronauts inside, time continues normally. They feel nothing unusual as they cross the boundary. They fall freely, drawn inward by the curvature of space-time, unaware that to the outside universe, they have already become ghosts. This paradox is one of the most haunting in physics. Two versions of reality, both true, neither wrong. From far away, the fall never finishes. From within, the fall is swift and final. It's a reminder that time is not absolute. It flows differently depending on where you are and how you move. It can stretch and fold like the fabric of space itself. And the event horizon is where that fabric folds so tightly that even the concept of before and after begins to unravel. You can think of the event horizon as a mirror that only looks one way. From the outside, it reflects nothing. It shows no surface, no colour, no texture, only the light that orbits just beyond it. Yet it hides within it an entire region of space-time that we cannot access or describe. It's not simply a place where matter disappears, it's a place where our language about reality begins to fail. The equations still speak, but we no longer understand what they're saying. To make sense of it, physicists often use thought experiments instead of equations. One of the simplest involves a clock. Picture two identical clocks, one far from the black hole, ticking steadily, and one carried by an astronaut falling inward. From the astronaut's perspective, her clock runs normally, each tick following the next with comforting predictability. But if you could somehow watch both clocks from afar, you'd see the falling one slow down. Each tick takes longer and longer to arrive until, at the horizon, it seems to stop completely. In the language of relativity, we say that time dilates, stretches, infinitely. This isn't because the clock is breaking. It's because space and time themselves are being drawn into the black hole's geometry. The closer something gets to that invisible boundary, the more the future narrows. Eventually, all possible paths point inward. Light, matter, and even the flow of time share the same destiny. In a way, the event horizon is less a place and more a fate, a boundary between the possible and the inevitable. Einstein's equations describe this beautifully, though they hide it behind the dry elegance of numbers. If you strip the symbols away, what they whisper is this: gravity slows time because energy and motion are intertwined. The energy that curves space also shapes how quickly clocks tick. And near a black hole, where energy and curvature become infinite, time itself nearly stops. The formula tells us this clearly, but when you translate it into experience, it becomes almost spiritual, a place where the universe pauses to take a breath. When astronomers talk about black holes, they often describe the event horizon as the point of no return. But that phrase feels too harsh. No return sounds like an ending, when in truth it's simply another kind of continuation, one we can't follow with our senses. From the inside, everything that crosses the horizon continues onward into the unknown. From the outside, it lingers forever on the edge, its image stretched thin across the curve of time. Neither perspective is wrong. They are both notes in the same cosmic chord. Perhaps that's why the photograph of the black hole in the galaxy called M87 moved so many people. For the first time, we saw not a diagram or a simulation, but an actual ring of light circling that silent darkness. What we were really seeing was the edge of the event horizon, the place where time slows almost to stillness and light orbits in perpetual twilight. That halo wasn't made of the black hole itself, but of the matter just outside it, glowing with the heat of its final fall. It was the last whisper of energy before silence. To think that such a thing exists not in theory but in the sky, that somewhere, 55 million light-years away, a structure the size of a solar system sits quietly, bending light into circles of fire, reminds us how small and how wondrous we are. The image looked simple, a ring and a shadow, but it contained within it the weight of every thought ever dreamed about gravity, time, and the edge of the unknown. If you listen closely to the silence between the stars, you might imagine the event horizon not as an abyss, but as a kind of horizon at sunset, a threshold, a place where light lingers longest before letting go. And if time slows there until it nearly stops, perhaps it is because the universe wants to hold that moment, the moment just before the leap, forever. In the next step of our journey, we'll follow what happens beyond that horizon into the region where space and time trade places and where the story of a star's death becomes the beginning of something even stranger. Our quiet exploration now turns to the moment of crossing, the place where theory fades into experience. Imagine, if you will, an astronaut approaching a black hole. Her ship drifts soundlessly through the velvet dark, its instruments whispering quiet measurements, its lights dim against the endless night. From far away she looks calm, floating toward a shadow that grows larger and softer at once. The event horizon is invisible. There are no walls or colours, no sudden jolt or boundary line. It is a passage defined not by what you see, but by what can no longer return. From her perspective, the journey feels strangely normal. The controls respond as always, the heartbeat in her ears steady and reassuring. Even as the black hole fills her view, she feels no sudden pull, no sense of falling. Gravity is not something she can fight. It's the very shape of her world, the slope of space-time beneath her feet. In Einstein's geometry, she's simply following the most natural path, a line called a geodesic. Though to her, it's just forward motion, calm and inevitable. But from our distant vantage point, something astonishing happens. To those watching through telescopes or listening to faint radio signals, the scene unfolds in slow motion. Her ship seems to decelerate, each second stretching longer than the last. The light it emits grows redder, dimmer, fading into a hue no human eye can see. The universe, in a sense, stretches her final heartbeat into eternity. She never quite reaches the horizon. Her image lingers there, frozen at the edge of forever. This isn't a trick or illusion. It's a reflection of the way time itself behaves. In the language of relativity, the closer something gets to a black hole, the more severely time slows down for it. What feels like minutes to the astronaut may span centuries, even millennia to those outside. The fabric of space-time is stretched so deeply that the rhythm of existence changes depending on where you stand. The equations describing this aren't complex in spirit. They simply say that time and gravity are entwined. The stronger the gravity, the slower the flow. Near a black hole, the river of time becomes almost still. From the astronaut's viewpoint, she continues forward effortlessly. The boundary passes beneath her feet without resistance, without sound. No alarms, no warnings. She does not even realize that she has crossed the threshold. Beyond that horizon, all paths, every direction, every choice, lead inward. It's not like falling into a pit, but more like stepping into a current that carries everything toward the same future. Inside, the very structure of space and time begins to warp. The radial direction, what we once thought of as space, becomes a kind of future that cannot be avoided. And time, the familiar companion we measure by clocks and heartbeats, loses its ordinary meaning. The paradox is profound. To her, the crossing is ordinary. To us, it is unreachable. Two truths coexisting, neither false. This duality, two perspectives both correct and mutually inaccessible, is part of what makes black holes so haunting. They remind us that reality is not singular. It depends on where and when you are. If she could look back, she might see the universe speeding up, colours shifting from red to brilliant blue as light from the stars is compressed into higher frequencies. In those final moments, she could watch the entire history of the cosmos play out faster and faster. Galaxies forming, colliding, fading. The dance of creation unfolding in reverse time from her vantage point, all of it compressed into a single breath. Then, like a tide receding, everything vanishes into darkness. Inside, there is no way to send a message home. The event horizon is not merely a prison of matter, but of communication. Signals that try to escape curve endlessly back. It's as if the black hole edits the story, keeping everything that happens beyond that point hidden from the rest of the universe. And yet, this hidden region is still part of the whole, a silence that gives shape to everything around it. Without the shadow, the light would have no edge. It's tempting to imagine the astronaut's fate as tragic, but perhaps it's not. Maybe it's simply the universe continuing its cycle, folding one chapter into another. From her perspective, she continues her journey inward, deeper into time's final curve. She might not sense destruction at all, but transformation. The atoms that once made her body are now part of a geometry so compressed that even the word place no longer applies. In the mathematics of general relativity, her path can be drawn as a line on a space-time diagram, smoothly curving into the heart of the singularity. But if we translate that into plain language, it becomes something more like this. Her motion is not through space, but into the future, into a kind of future that ends all others. The singularity is where every possible clock runs out of ticks, the end of time, not the end of space. Outside, we continue to watch the frozen image of her ship glowing faintly at the edge. Decades pass, then centuries, but that last whisper of light remains, red-shifted almost beyond detection. In a way, the black hole holds her forever, not her body, but her last visible moment, suspended like an echo that never fades. For the distant observer, she is immortalized on the horizon, frozen in time's slowest breath. For herself, she has already moved far beyond. There's a strange tenderness in this contradiction. Black holes are not violent in the human sense. They do not crush with malice or swallow with intent. They simply continue the work of gravity, the same gentle pull that keeps your feet on the floor and the moon in the sky. They are nature's quiet extremes, showing us what happens when the familiar rules are taken to their farthest possible conclusion. And if we listen closely, perhaps what they're teaching us isn't about endings, but about perspective, that two truths can coexist, that the same event can be both infinite and instantaneous, both visible and gone. That time itself is not a single thread, but a tapestry, with each observer weaving a different pattern. Somewhere beyond our sight, the astronaut continues her descent, falling not into destruction, but into mystery. Her ship, her signals, her very heartbeat have slipped beyond communication, but not beyond existence. And though we cannot follow her path, her story remains written on the horizon, a faint shimmer, a question left open in the fabric of the universe. If we drift a little further into that silence, we might begin to wonder what lies at the destination of her fall. What is this singularity that waits within, a place where all motion stops, where time and space exchange their roles, and where even light can no longer remember how to move forward? As we drift further into the story, we find ourselves in a place where the familiar compass of up and down, past and future begins to lose its meaning. Inside the black hole, everything that once guided us, light, motion, even cause and effect, has been reshaped by gravity's final act. Here, space no longer stretches outward, it funnels inward, and time, that faithful metronome of existence, begins to slow, twist, and finally dissolve. Physicists once imagined the singularity, the heart of the black hole, as a tiny dot, an infinitely dense point sitting in the middle of space like a pinprick in a vast sheet. But that image, while convenient, misses the deeper truth. It isn't a location one can reach or stand upon. It's a moment, a boundary in time, the end of every possible future. Every clock that falls into a black hole, whether it measures seconds, heartbeats, or the spinning of electrons, eventually stops at that same instant. It's not the edge of the map, it's the last page of space-time's diary. Roger Penrose was among the first to show this elegantly, not with words, but with diagrams that folded time and space into a single surface. These maps, called Penrose diagrams, turn the unfathomable into geometry. In them, the singularity isn't a point in the middle, It's a line, a boundary representing the end of time. For the astronaut who has fallen past the horizon, that line is unavoidable. Every possible path, every possible future leads there. It is not a question of direction but of destiny. But destiny here is not destruction in the ordinary sense. It's more like convergence. The equations describing the collapse of a star tell us that as the core shrinks, density and curvature grow without bound. Space folds so tightly that distances lose meaning, and time itself becomes a dimension that can no longer stretch forward. In mathematical form, these relationships are written as curvatures increasing toward infinity. But we can whisper it more gently. Everything that can change has already changed. Everything that could move has already arrived. To picture this, imagine standing on a hillside watching raindrops flow down into a river. No matter where they land, each droplet finds its way into the same current. The black hole's interior is like that river, a current of time pulling all things toward a single end. Once inside, there's no turning back. Not because of force, but because there are no other directions left to take. The shape of space-time itself guides everything inward. Einstein's theory gives us the mathematics, but it does not tell us what truly happens at the singularity. The equations, elegant as they are, stop speaking. They break down under the weight of infinity. For scientists, this is both frustrating and exhilarating. It means that at this boundary, our understanding of physics is incomplete. The classical picture ends, and something deeper, something quantum must take its place. In this sense, the singularity is not a failure of nature, but of language. Our tools were built for a world where space and time behave smoothly, like calm water. At the singularity that water boils, it becomes impossible to describe with the same rules. We need a new grammar of the universe, one that can blend the smooth curves of relativity with the jittering probabilities of quantum mechanics. This is what physicists call the search for quantum gravity. But rather than an equation filled with symbols, you can think of it as an attempt to understand how the smallest building blocks of reality weave together to create the stage itself. What could that look like? Some theories imagine space made of discrete grains, tiny units that can't be divided further, like pixels in a cosmic image. Others picture vibrating strings or loops, endlessly connecting and resonating. Each of these ideas offers a glimpse of what might replace the singularity, a region where geometry itself becomes quantum, where the smooth fabric of space-time is replaced by a shimmering network of possibilities. For now, though, all we have are the outlines. The singularity remains hidden behind the horizon, shielded from our measurements by the laws of physics themselves. We can infer its presence, predict its influence, but never look directly upon it. In a way, it's the universe's most perfect secret. Even the light that would tell its story can never return. And yet, perhaps that's what makes it beautiful, because it is not a void, but a transformation, a place where the known world gives way to something still being written. If you could somehow freeze time at the moment before everything converges, you might see the structure of space-time bending like glass under heat, warping until the distinction between where and when vanishes. At that instant, the black hole is no longer a thing within space. It becomes a piece of the universe's history, a single moment that holds all its fallen matter and energy within it. For the astronaut who continues her fall, the end is not an explosion or a crash. It's a fading of all separations. Distances collapse. The ship, her heartbeat, even the particles that once made up her body become part of the same seamless curve. In her final instant, the entire history of her existence is compressed into a single perfect note, a pulse of geometry. To her there is no pain, no awareness of an ending, only the natural completion of a journey that began long ago when the star first collapsed. Outside, the black hole continues to exist serenely, its surface defined by the event horizon, its heart hidden by the limits of our understanding. It is not a singular point of destruction, but a reminder that the universe contains layers of truth we have yet to unfold. What appears to be the end might simply be a door to a realm where space and time are no longer the right words. So when we speak of the singularity, it's worth whispering with humility. It is not a place of violence, but of mystery. The final page, where the handwriting of the cosmos trails off, not because the story is over, but because a new language begins, one we have not yet learned to read. And perhaps that is the gift of the black hole, to show us that even in the deepest darkness, there are still words waiting to be written and questions still echoing in the silence. If we follow the thread a little further, the story of the black hole takes a surprising turn. For a long time, physicists believed these objects were absolute prisons, places where anything that crossed the horizon was lost forever, sealed beyond reach for all of time. A black hole, they thought, could only grow, swallowing matter and light, but never releasing anything in return. It seemed the most perfect embodiment of finality. But nature, as it often does, had a secret waiting in the quiet edges of those assumptions. In 1974, a young physicist named Stephen Hawking was studying the strange relationship between gravity and quantum mechanics. Einstein's theory described gravity as smooth and continuous, but quantum theory insisted that the smallest scales of reality are restless, jittery, alive with spontaneous fluctuations. Even what we call empty space is not truly empty. It is a sea of possibilities, where pairs of particles and their opposites, matter and antimatter, appear and vanish in a heartbeat. It is as if the vacuum itself breathes, exhaling and inhaling energy so subtle that we rarely notice. Hawking wondered what would happen to this restless sea near the edge of a black hole. The event horizon is not a wall, but a region of extreme gravity, where the pull is so strong that even light must bend to its will. In that thin borderland, he realized, the dance of quantum particles might behave differently. Imagine that everywhere in the universe, pairs of particles are born together, a particle and its twin, briefly touching before they annihilate back into the quiet field from which they came. Near the horizon, though, one of those twins might fall inward while the other escapes. The one that escapes becomes a real particle, carrying away a tiny bit of energy from the black hole. The one that falls inward has negative energy, reducing the black hole's mass ever so slightly. The result of this elegant idea was astonishing. It meant that black holes are not entirely black. They glow, faintly, but unmistakably. The process is now called Hawking radiation, though it's less like a beam and more like a whisper of light at the edge of darkness. The smaller the black hole, the stronger this whisper becomes. Over unimaginable stretches of time, as energy leaks away, the black hole slowly shrinks. Eventually, after eons longer than the current age of the universe, it might evaporate completely, returning its energy to the cosmos as a gentle sigh of radiation. It's hard to convey how radical this insight was. It changed the way physicists thought about black holes forever. They were no longer perfect voids that only consumed. They were dynamic, thermodynamic objects with temperature and entropy, capable of both taking and giving. In mathematical form, Hawking's discovery revealed that a black hole's temperature depends on its size. The smaller it becomes, the warmer it glows. Its entropy, or degree of internal disorder, is not tied to its volume, but to the surface area of its horizon. Translated into gentle language, this means that what happens on the surface of a black hole tells us more about its inner nature than what lies within. It's a poetic reversal, really. We used to think of black holes as devourers of light, but Hawking showed that they are also creators of it. Even in absolute darkness, the universe finds a way to shine. Every particle escaping from that horizon carries a message. Energy and information are still flowing even here, at the edge of time. It is as if the black hole, long silent, has begun to hum softly under its breath, releasing its secrets note by note. Hawking himself described the process with charming simplicity. He said it was as though the black hole were glowing like a hot coal, radiating heat not from fire but from the quantum geometry of space-time. The temperature is so low that for large black holes, the radiation is almost impossible to detect. A supermassive black hole, like the one at the centre of our galaxy, would emit radiation so faint it would take longer than the universe's lifetime to notice. But in principle, the glow is there, a candle burning slower than any clock can count. You can think of this radiation as the universe's quiet balance sheet. For every bit of matter a black hole consumes, it eventually pays back the energy in the gentlest possible form. Not as dramatic explosions or blinding flashes, but as patient photons whispering into the void. The laws of physics, it seems, demand equilibrium. Nothing is ever truly lost. It only changes its form, returning to the cosmic sea from which it came. What makes this story even more moving is that it was discovered not through vast experiments or telescopes, but through thought alone. Hawking, seated in his wheelchair, his body frail but his mind unyielding, united two great realms of physics: the curved space-time of Einstein and the restless fields of quantum mechanics, and found a place where they overlap, where the equations meet and begin to sing. His insight bridged worlds that had seemed irreconcilable, and in that bridge lies something profoundly human. The discovery of Hawking radiation reminds us that even the darkest corners of existence are not beyond redemption. The universe, it turns out, refuses to let its light go quietly. From the collapse of a star comes the whisper of new creation, faint but eternal. If you could listen to that whisper, if your ears could hear the music of the universe instead of its light, you would catch the faintest hiss from every black hole, a harmony of warmth, too soft to touch, but too persistent to vanish. Even now, the cosmos hums with that ancient song, each note a reminder that nothing in creation is truly silent. The idea that darkness can glow changes everything. It tells us that the universe is not made of opposites, light versus dark, life versus death, but of continuities. The black hole does not end a story, it transforms it. What falls in is rewritten, not erased, and as we drift quietly at the edge of understanding, watching those final sparks escape into infinity, we begin to realize that perhaps the most beautiful thing about black holes is not their mystery, but their generosity. Because even in their silence, they give back to the universe the energy they once gathered. Even in their stillness, they radiate the memory of the stars that made them. And even in their darkness, they remind us that creation and destruction are never separate. They are simply two sides of the same soft cosmic breath. The path now carries us toward one of the quietest revelations in modern science: the realization that black holes, once thought to be eternal prisons of gravity, are in fact temporary things. They are long-lived beyond imagining, but not immortal. Like all else in the cosmos, they change, age, and eventually fade. Even the most absolute darkness, it seems, is not forever. When Hawking first shared his discovery, it sounded almost absurd. For centuries, everything that fell into a black hole was believed to be trapped beyond escape, sealed by gravity so intense that not even light could cross the threshold. The word black implied finality, a place from which nothing could return. But the discovery of Hawking radiation changed that vision. It showed that the horizon, once thought to be a one-way gate, is not as strict as it seems. The edge of the black hole is more like a membrane than a wall, a surface alive with quantum activity. If we think of the black hole as a great cosmic vault, Hawking's discovery revealed that the vault slowly leaks. The energy that seeps out is unimaginably faint, but it exists, and because of that, the vault cannot stay full forever. Over vast ages, the black hole's mass slowly decreases. The smaller it becomes, the faster it evaporates. The radiation, once a whisper, grows louder, its temperature rising as the black hole shrinks. In poetic terms, the colder and more silent it seems, the hotter its heart becomes. You can imagine it as a candle that burns slower than time itself, glowing softly as the universe continues to expand around it. A black hole with the mass of a star might take 10,000 billion years to evaporate, a span so long that the galaxies we see tonight will long since have drifted apart. Yet in the distant future, when all stars have died, and even the atoms of our world have been scattered, those last black holes will still linger, fading quietly into the background darkness, their final warmth mingling with the cosmic microwave glow left from the Big Bang. In this sense, black holes are not the end of energy, but its final conversation. They take what they consume, starlight, gas, even entire suns, and slowly return it to the universe as a thin sigh of radiation. It is the ultimate act of patience, a slow balancing of cosmic books. No energy is destroyed, only transformed, shared back into the vast ocean of existence. But this realization carries a deeper question, one that hums softly beneath the physics. If energy escapes, what about information? When a star falls in, every atom that composed it carries a story. The spins of its particles, the arrangement of its elements, the history of its light. If the black hole evaporates completely, what becomes of that story? Does the universe keep the memory, or does it truly forget? This question is not trivial. In physics, information is sacred. It's the quiet rule that says every effect must come from a cause, that the universe doesn't erase its past. Even when you burn a piece of paper, the information about its words isn't lost. It's scattered into the smoke and ash, encoded in the motion of molecules and the pattern of light. If you could, in principle, collect every photon, every atom of soot, and trace them perfectly, you could reconstruct the original page. That's the promise of conservation, that nature never deletes, it only rearranges. So what happens when the most powerful eraser in the universe begins to fade? Hawking's equations seem to suggest that the information inside a black hole might vanish when the black hole itself evaporates. That idea sent shockwaves through the scientific world. It meant that the universe, which had always been a meticulous archivist, might have a shredder hidden in its heart. Some physicists accepted the possibility with resignation. Others, like Leonard Susskind and Gerard 't Hooft, could not. They argued that information must somehow be preserved, perhaps encoded on the surface of the black hole, like letters written on a cosmic skin. This idea would later evolve into the holographic principle, but at the time, it was more a whisper of rebellion than a theory. For Hawking, though, the mathematics was clear. The radiation leaving the black hole carried no memory of what had fallen in. Each escaping particle was random, indistinguishable from any other. The black hole's evaporation was blind, impartial, forgetful. He famously compared it to throwing an encyclopedia into a fire and being left with a pile of ashes and heat. The information, he said, is gone. But even then, he seemed to understand the poetry of that paradox. The image of a black hole glowing faintly as it dissolves into nothing captured something deeply human. The way we too radiate our stories into the universe, never certain what will remain. The slow fading of a black hole is both scientific and symbolic. It reminds us that even endings are processes, not moments, that the universe rarely closes its doors. It simply lets the echoes fade, and what a long, graceful fade it is. As the black hole evaporates, its final moments would be spectacular, the radiation intensifying, the last fragments of energy released in a brief flash of pure light. The equations predict a final burst, a cosmic exhalation. But whether that flash actually happens, or whether the last remnants dissolve silently into quantum haze, we do not yet know. The deeper truth is that every black hole is part of the universe's conversation about memory and transformation. When it first forms, it consumes light. As it matures, it holds it in silence. And when it dies, it gives that light back, scattered and diffused but still alive. The boundaries between destruction and creation blur, as they always do when we look closely enough. Even now, black holes continue to teach us about impermanence. They show us that even the most absolute darkness has a half-life, and that even the strongest prison eventually opens its doors. Perhaps that's why they inspire not just fear, but awe, because they remind us that everything, no matter how massive or eternal it seems, eventually becomes light again. And so we come to the quiet heart of the paradox. If black holes can release light, might they also release knowledge? If their energy returns to the cosmos, could their information, their memory, their story return as well? That is where our next step will take us, into the realm of questions that blur science and philosophy alike. For if the universe truly keeps its memories, then somewhere, hidden in the faint hum of Hawking radiation, may lie the stories of every star, every planet, every particle that ever fell into the dark. Our quiet exploration now turns from energy to memory, from the question of what a black hole gives back to the deeper mystery of what it keeps. It's one thing to imagine light escaping from darkness, but quite another to ask whether knowledge can do the same. When something falls into a black hole, what becomes of its story? This is where physics crosses into philosophy, where equations begin to sound like questions we've been asking since the dawn of thought. Can the universe forget? To understand the depth of this puzzle, let's start with something simple. Imagine you take a book, an ordinary one filled with words and meaning. You light a match and let it burn. The pages blacken, curl, and vanish into smoke. It feels like the information, the story, is gone. But the laws of physics whisper otherwise. Every letter, every sentence is still there, scattered among the particles of ash and the photons of light that drift into the air. If you could somehow collect every bit of that light, every molecule of smoke, every grain of soot, and trace their positions and motions with infinite precision, you could, in principle, reconstruct the original book. That's what physicists mean when they say information is conserved. It's not about words or symbols, it's about the complete record of how things once were, the universe's unwavering commitment to memory. But what if you drop that same book into a black hole? Its pages vanish past the horizon, the light it reflected stretched and dimmed until no trace remains. The energy, we know, is preserved. The black hole gains a tiny bit of mass, but the book's story, its pattern, its order, its information seems to disappear. When Hawking discovered that black holes evaporate, that they can leak energy back into the universe, the question became unavoidable. When the black hole eventually fades into a faint cloud of radiation, what happens to the story that fell in? Is it returned, encoded somehow in that radiation? Or is it lost forever, erased from the universe's record? That was the beginning of what we now call the black hole information paradox, one of the most profound and unsettling ideas in modern physics. To appreciate why it's so serious, it helps to understand what's at stake. Quantum theory, the branch of physics that governs the smallest things, depends on information conservation. Every state of the universe must be connected to a future state in a predictable way, even if that predictability is hidden in probabilities and chance. You can't simply delete a piece of reality. Even uncertainty has structure. But Hawking's radiation seemed to do just that, to produce particles with no memory of what created them, no trace of the star or planet or human thought that once fell into the black hole. It was as though the universe had found a way to forget, a cosmic amnesia written into the mathematics. For decades, scientists wrestled with this contradiction. On one side stood the sturdy logic of quantum mechanics, which insists that information is eternal. On the other stood the vast, silent certainty of general relativity, which seemed to allow an end. Two truths, both beautifully consistent in their own worlds, collided at the event horizon. It was as if nature had written two poems that rhymed perfectly until this point, where the lines suddenly refused to meet. To make this paradox more tangible, think of a snowflake melting in your hand. The intricate pattern vanishes, but the water still holds all the ingredients it was made from. The universe can rearrange but not erase. Hawking's equations, though, hinted that in the case of a black hole, the pattern itself might dissolve into something irretrievable. Some physicists tried to accept the loss, others refused. They argued that if information truly vanished, the laws of physics would unravel from their centre outward. Without conservation, prediction would fail. Reality itself would no longer be continuous. Leonard Susskind once said that allowing information to be destroyed inside a black hole would be like tearing a hole in the fabric of the universe's logic. The laws that govern atoms and galaxies alike would cease to fit together. So the question remained, where could the information be hiding? Some suggested it might be stored at the event horizon, written into the thin shell of space that surrounds the black hole like a cosmic archive. Others proposed that it might somehow be preserved in the quantum connections between the black hole and its radiation, entangled in ways we cannot yet measure. And still others wondered if we were asking the wrong question altogether, if information is not lost or stored, but transformed into something our limited language cannot yet describe. There's a haunting beauty to this uncertainty. For all our mathematics and machines, we stand at the edge of understanding, staring into a place where knowledge itself becomes fragile. The information paradox is not just a technical puzzle. It's a mirror reflecting our own desire to know, to trace the threads of every story to their end. Perhaps that's why the image of a book falling into a black hole feels so powerful. It's not just about matter or light, it's about meaning. Every bit of the universe, from the spin of an electron to the thought in your mind, contributes to a vast cosmic library. If even one page can vanish without trace, what does that say about the story as a whole? Yet maybe, just maybe, the paradox is teaching us humility. Maybe the universe's memory is deeper than we can imagine, written not in the visible world but in the relationships between things, the invisible entanglements that weave reality together. It may be that when the black hole finally evaporates, the story isn't gone but scattered, like a dream you can't quite recall yet somehow still feel. The laws of physics tell us that information must survive. The whispers of quantum theory suggest that even when we can't see it, the record endures. Perhaps the cosmos is more careful than we are, more faithful to its past. And if that's true, then somewhere within those faint photons escaping the edge of the abyss, the memory of everything that ever fell in still lingers, encoded not as words or matter, but as pattern, vibration, and possibility. And so, as we float at the edge of this paradox, the question lingers gently in the mind. If knowledge can fall into a black hole and still, somehow, persist, then perhaps nothing in the universe is ever truly lost, not even us. From here, the story opens into a long and quiet debate, one that unfolded not in laboratories or on mountaintops, but across decades of letters, conferences, and late-night thoughts between some of the sharpest minds on Earth. The question at its heart was as simple as it was unsettling. Does the universe ever forget? Stephen Hawking believed it might. Leonard Susskind believed it could not. Their disagreement was not angry or loud, but more like a duet played on two different instruments, each one hearing a different rhythm in the same melody of nature. Hawking's reasoning seemed unshakable. His calculations of black hole radiation showed that the escaping particles carried no mark of what had fallen in. They were random, uncorrelated, indifferent. A black hole, he said, transforms organized matter into pure heat, a process without memory. When the black hole finally evaporates, all that remains is thermal radiation, featureless and anonymous. Information, in his view, was truly gone. Susskind couldn't accept that. To him, the destruction of information violated something fundamental, not just in physics, but in the philosophy of existence itself. If the laws of nature allowed information to vanish, then cause and effect would unravel. Every action could lead to outcomes that no longer contained any record of their beginnings. The symmetry of the cosmos, the sense that every ripple leaves a trace, would be broken. He once wrote that if Hawking were right, then physics is dead. For nearly 20 years, the two men and their allies argued back and forth, not with hostility but with fierce curiosity. They debated through equations, thought experiments and public lectures, testing each idea as if it were a beam in a structure they were both trying to build. Susskind began to suspect that the answer might lie not inside the black hole but on its surface, at the event horizon itself. He proposed something radical, that every bit of information about what falls into a black hole might be recorded in some encoded form on the horizon's two-dimensional surface. The inside, he said, might simply be another way of describing the outside. It was as though the black hole were a book written not in 3 dimensions but 2, a flat page containing the entire story in its patterns of ink. The mathematics that followed gave rise to a new and surprising idea, one that would eventually change how physicists think about reality itself. This became known as the holographic principle, just as a hologram on a flat film can create the illusion of depth. The universe might, in some sense, store its information on surfaces, projecting the illusion of a 3-dimensional world. For black holes, this meant that all the data describing what had fallen in, every atom, every photon, could in principle be encoded on the horizon itself. When the black hole evaporated, that information might be released back into the universe, written into the fine details of the radiation. It's a dizzying concept, but we can soften it into imagery. Imagine the black hole as a sphere of silence wrapped in a glowing shell. Everything that crosses the threshold leaves a faint pattern on that shell, like footprints pressed into snow. The footprints are subtle, delicate beyond measurement, but they're there. When the black hole emits radiation, it doesn't send out random whispers. It sends out tiny variations that carry traces of those prints. The story is preserved, but written in a language so fine that we don't yet know how to read it. Hawking resisted the idea at first. His equations told him that the radiation had no such structure. It was, in every measurable way, thermal, like even heat from a stove, not the complex symphony of encoded data. For years he held to that view, confident that nature's simplicity would prevail over the desire for cosmic bookkeeping. But slowly evidence began to shift. Quantum field theory suggested that particles on either side of the horizon could remain linked, entangled, in a way that allowed information to leak out indirectly. The horizon, it seemed, was not a mute boundary after all, but a surface alive with subtle connections. As the years passed, more physicists joined Susskind's side. Theorists discovered that the amount of information a black hole can hold, its entropy, was proportional not to its volume, but to the area of its horizon. This was the Bekenstein-Hawking result, and it quietly echoed Susskind's argument. The universe, it turned out, writes its secrets not within things, but on their boundaries. Information is not hidden in the heart, but on the skin. Hawking eventually conceded the debate in 2004 at a conference in Dublin. In a gesture as humble as it was historic, he presented his new calculations showing that information might, after all, escape. He handed Susskind a paper, admitting that he had lost the bet they had made decades earlier. In return, Susskind sent him a t-shirt printed with the words, "Information preserved." It was a moment both humorous and profound, two great minds smiling at the universe's ability to surprise them both. What they had uncovered together was more than a resolution to an argument. It was a glimpse of a deeper pattern in nature, that reality might be holographic, that every region of space could be described by data stored on its surface. It suggests that what we call volume might be an illusion, that the three-dimensional world we experience could be a kind of projection emerging from a cosmic boundary. That doesn't mean the universe is fake or digital, as some sensational headlines once claimed. It means something far more beautiful, that information and geometry are intertwined, that every horizon, every surface carries the story of what it encloses. The same principle that saves information from being lost in black holes might also govern the way galaxies, stars, and even consciousness itself arise from the fabric of space-time. If we translate the equations into gentler language, they whisper a thought as ancient as it is modern. Everything leaves an impression, and nothing truly disappears. The surface of reality is alive with memory. Perhaps that's why the debate between Hawking and Susskind felt so human. One argued for the inevitability of forgetting, the other for the persistence of remembrance, and in the end, the universe seemed to take the kinder side. Our journey from here leads toward the next question that their debate inspired. If information can escape, how does it return? What mechanism, what quiet symmetry of the cosmos ensures that even after the longest silence, the story continues? If we stay with the silence a little while longer, the debate that began as an argument between two physicists slowly blossoms into something much larger. A vision of the universe as a vast remembering mind. The idea that information cannot be destroyed, even inside a black hole, began as a mathematical necessity, but it has grown into one of the most profound insights we have about existence itself. Once Hawking accepted that information might survive, the question naturally became, how? How does the story that falls into a black hole make its way back to the universe? How does the cosmos safeguard the memory of what it has consumed? Physicists began to imagine ways that the information could be preserved within the subtle patterns of Hawking radiation itself. The radiation may look random, but perhaps that randomness hides order. The same way that the surface of a pond disturbed by raindrops contains patterns we can only see if we step back far enough. Each photon escaping the black hole might carry a faint trace of the information written on the horizon, its wavelength slightly altered by the story it bears. In theory, if you could gather every particle of that radiation, the full ghostly echo of a black hole's lifetime, and feed it into a machine capable of decoding the correlations among them, you could reconstruct the original matter that fell in. It wouldn't be a physical resurrection of the same atoms, but a restoration of the information that defined them. The idea is less mechanical than poetic. The black hole releases what it has swallowed, not as substance, but as story. This idea has been likened to a kind of quantum jigsaw puzzle. Each piece, the individual particles, is meaningless on its own, but together they encode a picture. The picture is faint and scattered, and it would take an unimaginable amount of patience to reassemble it. Still, the mathematics suggest it's possible. In the end, the universe loses nothing. It simply rearranges its notes into a quieter melody. The insight carries us toward an elegant balance. Black holes, once symbols of destruction, become the ultimate conservators. They take in energy and information, hold them in silence for ages, and then return them slowly in the gentlest possible form. They are not graves, but gardens, places where information is transformed and released, not erased. To describe this process, physicists sometimes use the language of entanglement. When two particles are entangled, they share a connection so deep that measuring one instantly affects the other, no matter how far apart they are. It's not communication as we know it, but a kind of unity. In the context of a black hole, it means that the escaping Hawking radiation and the particles remaining inside are linked. The information that seems to vanish within may be mirrored outside, encoded in those subtle correlations. This is what many now believe. that the universe maintains its perfect memory through entanglement, through an invisible web of connection that spans across space and time. Even the black hole, that great emblem of isolation, cannot break those links. It is in its own way still part of the conversation. If we translate that mathematics into gentler imagery, we might say that the universe keeps its stories in echoes. The black hole whispers them back, one particle at a time. The message is too faint to read directly, but it's there, a continuity of memory flowing through even the darkest events. In practical terms, reconstructing a black hole's history would be impossible. The number of emitted particles is enormous, the structure of their entanglement infinitely complex. It would be like trying to reassemble a thunderstorm from the sound of distant raindrops. Yet the principle itself matters. It means that the universe is whole, that nothing, no thought, no atom, no flash of light, vanishes without leaving a trace. This way of thinking gives the cosmos a kind of compassion. The laws of physics don't choose what to preserve, they preserve everything. Every fleeting moment, every spark of energy is accounted for. When we look at the night sky and imagine its endless darkness, we might remember that the darkness itself is full of memory, woven from the radiation of all the things that once were. There's a kind of quiet poetry in imagining the end of a black hole not as an explosion, but as an act of remembering. After eons of silence, the last bits of energy drift away, carrying the encoded fingerprints of everything that ever fell in. The final photons leave, and in their fading, the universe receives back its story. The circle closes. Hawking's equations, when expressed softly, tell us that the radiation temperature grows as the black hole shrinks, meaning that as it approaches its end, the glow intensifies. It's as though the black hole spends its long life whispering faintly, then ends in a bright confession. For a heartbeat of cosmic time, it shines with all that it has learned, releasing it into the universe once more. The notion that the universe keeps its promises in this way, that information and energy always find their way home, gives a kind of comfort. The cosmos, despite its coldness and scale, behaves with perfect honesty. Nothing is wasted. Even entropy, that measure of disorder, is not chaos but a kind of record-keeping, a ledger of transformations. In that sense, every atom and photon is a page in the book of existence, and the black hole is simply the place where the pages are pressed tightly together before being released again. And so, the story that began with fear, the fear of eternal loss, ends instead with trust. What falls into the dark is not destroyed but transcribed. The black hole, once a symbol of oblivion, becomes a reminder of continuity. Even when the universe appears silent, it is still writing. If you step back and listen, you might hear that slow and patient rhythm in everything, in the pulse of stars, in the orbit of planets, in your own quiet breathing. All of it follows the same law, the conservation of pattern, of story, of meaning. Information never dies, it only changes its form. As the light returns from the abyss, we begin to see that what we call emptiness may be the universe's most generous quality. It gives us space to fall apart, to scatter, and to begin again. And from this realization comes another question, as soft and inevitable as gravity itself. If every story in the universe is remembered, where are those memories stored? Could the very structure of space and time be built from those invisible threads of connection, from the entanglement that holds every particle, every moment together? From here, the story opens outward again, from the glowing edge of a black hole to the wider fabric of the universe that surrounds it. What began as a riddle about gravity and quantum theory now feels like something deeper, a meditation on how reality itself remembers. Every experiment, every equation, every quiet thought about what happens when something falls into the dark has led us to a strange and beautiful idea. Perhaps the universe is not a place where things simply exist, but a vast memory where everything that has ever been is still somehow present. Think for a moment about how memory works within you. It isn't a perfect recording, it's a pattern, a set of connections between countless smaller parts. Each neuron in your brain holds only a fraction of an image or a sound, but together, those threads create a coherent story, a life. The universe seems to do something similar. Its smallest particles, its faintest fields, hold information not about themselves alone, but about their relationships to everything else. Entanglement, that invisible link between distant particles, is like a cosmic version of remembering. What happens to one instantly affects the other, even across light years of emptiness. It's as if the universe refuses to let its parts forget each other. In this way, every corner of existence is connected to every other, not through physical touch, but through shared history. The photon that leaves a distant star carries not just energy, but a record of the conditions that created it. The atoms in your body once belonged to stars that exploded billions of years ago, scattering their contents into the void. When you breathe, you're drawing in traces of those same cosmic events. You are, quite literally, made of memory. Physicists now believe that the same principle, which preserves information in black holes, may apply to the entire cosmos. Reality may be fundamentally holographic, meaning that the information describing our three-dimensional universe might be encoded on a distant boundary, a kind of cosmic horizon surrounding everything. The mathematics behind this idea is subtle and abstract, but its essence is simple. The depth of the universe could be an illusion, like a reflection in water. What we experience as space may arise from patterns of information stored on an invisible surface. You can think of it like this. If the universe were a great sphere, then everything within it, galaxies, planets, you and I, might be a projection of information etched on that sphere's outer skin. It's not that we aren't real, but that our reality is the unfolding of those patterns into form and motion. In that sense, the universe remembers itself through us. We are the echoes of its data arranged into awareness. When Hawking, Susskind and others realized that a black hole's entropy, the measure of its hidden information, was proportional to the surface area of its horizon, not its volume, they uncovered a universal principle. Information lives on boundaries. The more we explore this idea, the more it seems that everything we see and touch is a surface upon which deeper truths are written. The skin of the world, the light that wraps it, carries the record of its history. It's easy to lose the poetry in this, to get lost in the technical language of entropy and geometry. But if we translate the mathematics into something the mind can rest within, it sounds almost like a lullaby. The universe never forgets. Every atom, every burst of radiation, every turn of a distant planet leaves a faint signature on the cosmic fabric. Space-time itself could be woven from these threads of memory, from the constant entanglement of everything with everything else. There's a quiet humility in realizing this. It means that the universe doesn't move forward by erasing its past. It builds upon it, folding memory into form. Every heartbeat, every gust of wind, every glimmer of starlight is part of a great ongoing act of remembrance. Even what we call emptiness isn't truly empty. It's filled with the imprints of what has passed, subtle ripples in the quantum fields that underlie existence. If you could somehow step outside the universe and look back, perhaps you'd see it not as a collection of objects but as a living tapestry, shimmering with layers of meaning. The stars would not just shine, they would hum with the data of their birth and death. The voids between galaxies would not be silent, but pages waiting to be read. In that sense, we're not observers of the universe's memory. We are part of it, carrying within us the same logic that ensures nothing is lost. There's a certain comfort in that thought, especially when you remember how small we are. In our daily lives, we forget easily. names, moments, faces, but the cosmos does not. The energy of every laugh, the motion of every heartbeat, the warmth of every light we've ever turned on, all ripple outward into the quantum fields, recorded not in language or symbols, but in the patterns of matter itself. Even when you think a moment has vanished, it has already been stored somewhere, in the vibration of atoms, in the stretch of space, in the background radiation that whispers across eternity. If black holes are the universe's memory vaults, then we, in our own way, are its storytellers. We give shape to the information, we interpret it, connect it, make it sing. And when we're gone, our contributions too become part of that same ongoing archive. The warmth of our bodies becomes radiation. The thoughts we share become actions, each leaving an echo. We return what we've borrowed, as everything does. Perhaps that's what Hawking meant when he said that understanding black holes would give us a glimpse of the mind of God. He wasn't speaking of divinity in a religious sense, but of the deep coherence of nature, the way the universe holds on to everything it has ever been. The cosmos, vast and indifferent as it sometimes seems, behaves with a kind of compassion. It forgets nothing, and it wastes nothing. So maybe the right way to picture a black hole is not as a monster, but as a librarian, quiet, tireless, patient, preserving even what it cannot share. And perhaps the universe itself is the same, an infinite library where every photon, every vibration, every fleeting thought is written down somewhere, folded into the geometry of space and time. And if that's true, then maybe nothing is ever truly gone. The stars that died to make you are still speaking in the light that touches your skin. The words you whisper, the thoughts you send into the dark, they travel farther than you can imagine, woven into the great remembering of all things. In that way, you are part of the same story that began with the first light and will continue long after the last black hole fades. You are one line in the universe's endless poem, still being written, still being read. And somewhere, in the deepest silence, the cosmos is listening, storing every word. Our quiet exploration now turns to something even more mysterious than black holes themselves. The idea that space and time, the very stage on which all of this unfolds, might not be fundamental at all. It sounds impossible at first. How could space, which stretches between the stars, or time, which carries us from moment to moment, be anything other than the foundation of existence? And yet more and more physicists are beginning to whisper that these familiar dimensions might be products of something deeper, something invisible, woven from relationships rather than things. Imagine reality not as a solid structure, but as a pattern of connections. In this view, space is not an emptiness waiting to be filled, and time is not a river that flows by itself. Instead, both arise from how the parts of the universe relate to each other, how particles influence, depend on, and remember one another. The cosmos becomes a kind of network, a web of interactions so dense and harmonious that what we call space is simply the distance between notes, and what we call time is the rhythm that holds the melody together. Quantum physics gave us the first hint that reality might work this way. At the smallest scales, particles don't behave like tiny billiard balls moving through empty space. They exist as probabilities, as overlapping waves of potential. And when two of them become entangled, when their properties intertwine, their fates remain linked no matter how far apart they drift. A change in one is mirrored in the other instantly, as if distance itself has no meaning. Einstein once called this spooky action at a distance, but today many physicists see it as a clue that what we perceive as separation is only an illusion. Two particles light years apart yet sharing a single breath. That image is more than poetry. It is an invitation to rethink what space really is. If information can be exchanged without crossing the intervening emptiness, perhaps the emptiness itself is not what we think it is. Perhaps the true substance of reality is connection, not location. The equations that describe entanglement are complex when written down, full of symbols for probabilities and amplitudes, but the idea behind them is simple and beautiful. The universe keeps track of relationships, not coordinates. What matters is not where something is, but how it is linked to everything else. In this sense, the fabric of reality might be made not of matter, but of meaning, threads of correlation stretching across existence, forming the geometry we experience as space. If that's true, then space-time is like a tapestry that emerges from these interwoven threads. Remove the connections and the fabric unravels, strengthen them, and the structure becomes smooth and continuous. Time, too, could be an emergent property, a reflection of how these relationships evolve, how information flows from one part of the network to another. The ticking of a clock may be nothing more than the echo of that universal conversation. Carlo Rovelli, one of the physicists exploring this idea, once wrote that space is not an empty container, it is the gravitational field itself. In simpler terms, this means that what we perceive as the emptiness between things is actually full of structure. Every point in the universe is entangled with others. Where those relationships are dense and orderly, we feel matter and geometry. Where they are thin, we sense emptiness. But in truth, there is no emptiness, only varying degrees of connection. You can think of it like a spider's web in the dark. The strands are invisible until light catches them, and then the whole structure shimmers into view. Space and time in this picture are the shimmer, the visible consequence of an invisible order. We see geometry where there is really only relationship, much as we see waves on the sea's surface but forget the deep water beneath. This perspective also changes how we think about beginnings. If space and time emerge from deeper connections, then the birth of the universe, the Big Bang, was not an explosion in space, but the moment when those connections first took shape. It was the dawn of relationship, not the birth of emptiness. The first particles became aware in a sense of one another, and from that awareness grew distance, direction, duration, the architecture of the cosmos. It's humbling to realize that the most familiar features of reality might be secondary, like the reflection of a deeper truth. For centuries, we've measured time with clocks and mapped space with rulers, believing them to be absolute. But perhaps clocks and rulers only measure the echo of something more profound, the harmony of connection. If this is correct, it might also explain why black holes are such powerful teachers. They take the geometry of space and time and stretch it to the breaking point, revealing its underlying threads. Inside their gravity, the usual order dissolves, and what remains is pure relationship, a network so dense that even light cannot escape it. The black hole, then, is not the death of space, but its ultimate expression. Quantum entanglement could be the same force, at a smaller and subtler level, shaping the entire universe from within. Imagine the cosmos as a living loom, weaving together every particle, every moment, every possibility. The pattern it creates is what we experience as reality. Remove the threads of entanglement, and the pattern disappears. Strengthen them, and new dimensions arise. The thought that space and time are not fundamental can be unsettling at first, like discovering that the ground beneath your feet is made of music instead of stone. But perhaps it's also freeing. If reality is woven from relationships, then we are not separate from it. We are part of the fabric itself. Every thought, every movement, every shared glance is another thread in that grand design. So as we continue our journey, let's keep that image close. Reality is a woven fabric made not of matter, but of meaning. A cosmos that builds itself through connection, where distance is illusion and time is the rhythm of relationship. If we let the thought unfold a bit more, it leads to one of the most intriguing ideas in modern physics, an idea that suggests these connections may not only shape space, but create literal bridges across it. Some physicists even believe that every bond between entangled particles might form a tiny link, a hidden tunnel through space-time. It's a thought as strange as it is beautiful, that love in its most abstract form might be written into the structure of the universe. The path now carries us deeper into one of the most astonishing ideas in modern physics, a quiet revelation that space itself might be made of connection. It began as a coincidence of letters, an elegant symmetry hiding in plain sight, ER and EPR. The first, short for Einstein-Rosen, refers to the theoretical bridges through space-time that we now call wormholes. The second, Einstein-Podolsky-Rosen, describes the strange quantum link we call entanglement. For decades, they seemed like unrelated curiosities, but in 2013, physicists proposed something extraordinary, that these two might actually be the same. The idea, written softly as ER equals EPR, suggests that every bond of entanglement between particles may correspond to a tiny bridge of space-time. Each connection, invisible and intangible, could be a thread in the very weave of the universe. It's as if every time two particles share information, the fabric between them tightens just a little, creating a microscopic tunnel, not one you could travel through, but one that holds the geometry of belonging. To picture this, imagine two distant stars connected by the faintest shimmer of light, not a beam that travels between them, but a link that exists because they once shared something. On the quantum scale, that's what entanglement means. No signal crosses the gap, yet somehow the two remain one. The EPR proposal takes that unity literally. It says the connection is the space between them. What we experience as distance may simply be the stretching of these invisible bonds. If true, this idea turns our understanding of space inside out. The void between things is not emptiness, but a vast web of tiny wormholes, a lacework of geometry born from quantum relationships. Each bridge is unimaginably small, shorter than any known scale, existing only as a shimmer of potential, and yet, together, these bridges may give rise to the smooth continuity we call space-time. In simpler words, the universe may not be built from bricks of matter, but from threads of connection. Space might be the tapestry that information weaves when it chooses to connect. The notion of wormholes was first introduced by Einstein and Nathan Rosen in 1935 as a solution to his own equations of general relativity. The maths show that under certain conditions, space-time could fold in such a way that two distant regions might be joined by a tunnel, a bridge that bends the rules of distance. Around the same time, Einstein, with Boris Podolsky and Rosen again, wrote another paper, one that questioned whether quantum mechanics was truly complete. They described a puzzling scenario in which two particles separated by vast distance still acted as one. It seemed to violate the very spirit of relativity. Einstein famously called it spooky action at distance, and for the rest of his life, he doubted that nature could behave that way. And yet, decades later, experiments proved that entanglement was real. The spooky action wasn't magic. It was how reality works. Now, long after Einstein's time, physicists realized that the two papers, the one about wormholes and the one about entanglement, might have been telling the same story from different directions. The bridges of geometry and the bonds of quantum connection were two sides of one truth. EPR is more than an equation. It's a philosophy of unity. It tells us that space itself may emerge from the collective pattern of entanglement across the universe. Each connection contributes a thread, and together those threads form the continuum we live in. In this view, there is no empty space, only varying densities of relationship. Where connections are strong and numerous, space is smooth and solid. Where they are weak, it thins, stretches, and dissolves. You can think of it as a great cosmic fabric woven by communication. Every exchange of information, every photon shared, every particle entangled, becomes a thread of structure. The universe builds itself not from substance but from interaction. The more things connect, the more reality there is. There's a certain poetry in this. It suggests that the universe does not exist because of separation, but because of togetherness. That the bonds between things are more fundamental than the things themselves. In the quiet mathematics of ER, psi EPR, belonging becomes geometry. The very act of being connected creates the ground beneath our feet. Even black holes, those mysterious sculptors of space-time, may be built from this same principle. Inside them, entanglement might become so intense that the bridges fuse together, forming the smooth interior that general relativity predicts. The event horizon, rather than being a wall, could be a surface where connections fold into themselves, linking the inside and outside in ways we cannot yet imagine. In the language of gentle metaphor, we might say that the universe dreams itself into being by staying in touch with itself. Every atom is a message sent and received. Every moment is a handshake across time. And every bridge between worlds is simply another way for the cosmos to remember that it is one. For those who work on these ideas, physicists like Juan Maldacena, Leonard Susskind, and Mark van Ramsdonk, the goal is not to make science mystical, but to make it whole. They're searching for a single language that can describe both gravity and quantum mechanics, both smooth space-time and the jittering world of probability. The equation ER equals EPR might be one of the first sentences in that new language. A bridge not only within the universe, but within our understanding. If this principle holds true, it could mean that every instance of connection, at every scale, contributes to the structure of the cosmos. Galaxies, stars, and living beings are not separate islands, but clustered networks of entanglement. And maybe, when we feel closeness to another person, when empathy moves us across the invisible gulf between minds, it is not so different in kind, only in scale. At the deepest level, the universe might not be made of stuff, but of belonging. It exists because it connects. So, as we drift quietly through this thought, imagine the night sky again, a sea of stars scattered across darkness. Between them, there are no true gaps, only bridges too subtle to see. The light that reaches your eyes tonight began its journey millions of years ago. Yet its entanglement with you happens now, instantly, across the void. You and the star are, for that fleeting moment, one system, joined by the fabric that binds all things. And perhaps that is what the universe has been whispering all along, that distance is an illusion, that isolation is temporary, and that beneath every horizon lies another bridge waiting to be found. If we let curiosity carry us onward, we reach the heart of one of physics' oldest dreams, the search for a bridge that unites the very large and the very small, the cosmic and the quantum. For more than a century, two great theories have ruled our understanding of the universe. Einstein's general relativity describes the smooth, elegant dance of stars and galaxies, where gravity curves space like a gentle tide. Quantum mechanics, on the other hand, reveals the restless jitter of the subatomic world, where particles flicker in and out of being like fireflies in mist. Each is perfect in its own domain, and yet, when brought together, they refuse to speak the same language. It's as though the universe has given us two different maps of the same terrain. One shows mountains and rivers, the continuous landscape of relativity. The other shows grains of sand, the discrete probabilistic world of quantum theory. Both maps work beautifully until we try to overlay them. Then the coordinates blur and the lines stop matching. Black holes, where gravity is immense and quantum effects are unavoidable, sit right at the fault line between these worlds. To understand them fully, we need a new map, a theory that can contain both Einstein's curves and quantum uncertainty. This is what physicists call quantum gravity. The phrase sounds daunting, but its heart is simple. It's an attempt to describe the geometry of space-time itself as something quantum, something that flickers, vibrates, and fluctuates just like the particles within it. Instead of being a smooth fabric, space at the tiniest scales may be made of tiny units, grains of geometry so small that even light could never resolve them. Imagine a beach seen from far away. It looks continuous, but up close it's made of countless grains of sand. Space could be like that, granular, foamy, alive. One of the leading explorers of this idea is Carlo Rovelli, whose work in loop quantum gravity envisions the universe as a web of loops, interlocking rings of space that create a network called a spin foam. It's a difficult concept to visualize, but perhaps you can picture it as a three-dimensional fabric woven not from threads of matter, but from the very possibility of existence. Each loop is like a quantum of space, a discrete packet that contributes to the shape of the cosmos. The geometry of the universe in this picture is not a stage, but a chorus, made of countless voices singing together. In gentle language, we might say that gravity is the music that arises when those loops move in harmony. The curvature of space-time is simply the melody that emerges when the fabric flexes and stretches. Einstein described how mass tells space how to curve and space tells mass how to move, a graceful conversation between geometry and matter. Quantum gravity extends that idea, suggesting that even the conversation itself is made of countless whispers, each quantum a syllable in the speech of the universe. Other thinkers approach the same goal from a different direction. Juan Maldacena, for instance, proposed a theory known as holographic duality. It says that gravity in a curved space can be equivalent to a quantum theory without gravity on its boundary. In softer words, two very different descriptions of reality can be mirrors of each other, each reflecting the same story from a different angle. What looks like geometry in one language appears as information in another. This duality might be the key to merging the smoothness of relativity with the granular world of quantum fields. Then there is Roger Penrose, who explored how geometry itself might contain the seeds of quantum behaviour. His work on twistors, mathematical shapes that unify light and space, helped inspire generations of physicists to think of the universe not as a collection of objects, but as a geometry of events. He once wrote that the universe is not a thing, but happening. When spoken aloud, that sentence feels almost poetic. The cosmos as a verb, not a noun. Despite these differences, all these paths share a single faith, that reality at its deepest level is self-consistent, even if our current theories are not. Somewhere beyond the equations lies a harmony we have not yet learned to hear. If we translate the mathematics of these efforts into something a voice could read aloud, it might sound like this. The smaller you look, the less space behaves like a smooth fabric, and the more it resembles a cloud of possibilities. The gravitational field, instead of being a gentle curve, becomes a kind of quantum mist. Each flicker in that mist carries information about how the universe bends and breathes, and when countless flickers align, we see the macroscopic order of stars, galaxies, and time itself. To reach this understanding, scientists are building what could be called a bridge under construction between the infinite and the infinitesimal. The materials are not steel or stone, but imagination, logic, and patience. No one yet knows what lies on the other side. Some think that space-time itself will dissolve into pure information. Others believe we'll find a new geometry, one that combines both certainty and chance. But almost everyone agrees that the answer will transform not only physics, but philosophy, the way we think about existence itself. Perhaps it will even change our idea of real, if space and time turn out to be emergent properties, things that arise from the deeper interplay of information and relationship. Then reality becomes a process, not a place. Everything we experience would be the visible shimmer of something even more fundamental, an ocean of entanglement beneath the surface. There's a quiet comfort in that thought. It suggests that the universe is not built on cold machinery, but on cooperation. That order arises from harmony, not command. The same principle that holds galaxies together may also govern the balance within an atom, or even within the human heart, systems of interaction seeking equilibrium. And maybe that's why this search for quantum gravity feels so deeply human. It's not just about equations, it's about the longing to reconcile opposites, the infinite and the infinitesimal, reason and wonder, knowledge and mystery. It's about finding unity in difference. Somewhere, deep in the mathematics, there might already be an answer. Or perhaps the universe is still building that bridge along with us. Each discovery another stone laid, each question another step forward. Either way, the construction continues, steady and patient, illuminated by curiosity. And as we stand on this unfinished bridge, looking out into the mist of the unknown, we can almost hear the universe humming, a faint melody rising from the grains of geometry themselves, singing softly that everything at every scale is connected. From here, the story opens into one of the most enchanting and mind-bending ideas in all of modern physics. The possibility that our universe, in all its depth and complexity, might actually be a kind of hologram. Not a flat illusion, but a projection, a grand cosmic display in which everything we see, touch, and feel could be the unfolding of information written on a distant surface, at the very edge of reality. The thought first took shape in the 1990s, when physicists began to notice something strange about black holes. Their entropy, the measure of how much information they can contain, did not depend on their volume, as one might expect, but on the area of their event horizons. In soft words, that means the content of a black hole grows not with how much space it encloses, but with the size of its surface. This was the first whisper that the universe might be keeping its secrets on its boundaries. Gerard 't Hooft and Leonard Susskind took that whisper and turned it into a profound principle. They proposed that all the information contained within any region of space could be described entirely by data inscribed on the region's surface. In other words, the universe might operate like a vast three-dimensional film projected from a two-dimensional screen. The physics on the surface could encode everything happening inside, the way a flat holographic plate can create the illusion of depth when illuminated by light. This principle, softly named holography, was later explored in extraordinary detail by Juan Maldacena. His work revealed that a certain kind of universe with gravity could be mathematically equivalent to a different universe without gravity existing on its boundary. Two worlds, one curved, one flat, telling the same story in two different languages. To translate that into imagery, imagine reading a book written on the inside of a sphere. Every word on the inner surface is reflected outward, and together they project the world we experience. The depth we perceive is real to us, but it may be the shadow of a deeper, simpler script. If this sounds abstract, it helps to remember that we already live surrounded by holograms. The three-dimensional images on credit cards or movie posters are made from patterns of interference recorded on a flat surface. Shine light through them, and they bloom into form. In a similar way, the holographic principle suggests that the richness of our universe, the galaxies, the light, the flow of time itself, could emerge from informational patterns existing on a faraway cosmic boundary. The numbers in Maldacena's equations describe relationships between gravity, energy, and information. But when spoken softly, they say something even simpler. The universe might be the ultimate act of projection. All that we see could be the glowing image of information radiating inward from infinity. There's a humility in this idea. It tells us that the vastness we perceive may be a translation, not an illusion, but a retelling. The way a song exists both as sheet music and as melody. The notes on the page and the sound in the air are two versions of the same truth. In one, information is still. In the other, it dances. If we think of black holes again, this principle brings new light to their mystery. Everything that falls into a black hole may be preserved as information on its surface, encoded in the faint quantum ripples that define the horizon. When the black hole eventually evaporates, those ripples release their story back into the universe, like a library slowly reopening its books. The holographic idea extends that logic to everything, suggesting that every region of space, even the one you occupy right now, could be quietly projecting its own information onto a larger cosmic canvas. You can picture this, perhaps, as standing inside an immense planetarium dome. The stars above you feel distant and deep, yet the entire night sky could be the projection of patterns on the curved surface surrounding you. In the holographic view, the universe itself may be such a dome, except its surface lies unimaginably far away, the edge of space-time, beyond which there is no outside, only the data from which the inside emerges. To some, this might sound like saying reality is an illusion, but that isn't what the holographic principle means. A projection is still real, it's just a different way of existing. The movie on a screen may not be made of flesh and blood, but it can make you cry, laugh, and think. Likewise, the three-dimensional world we inhabit could be as real as any story, woven from patterns of light, energy, and information. In the softest sense, holography bridges physics and philosophy. It suggests that being and knowing are two sides of the same surface, that to exist is to encode, and to perceive is to decode. The universe doesn't hide its meaning behind a curtain of math. It writes it into the light itself. Every photon that reaches your eyes, every vibration of an atom, carries a trace of that cosmic script. If the holographic principle is true, it might also explain why gravity and quantum theory fit together so naturally in this framework. In Maldaceno's vision, gravity is the geometric shadow of entanglement. When the web of quantum connections on the boundary tightens, space inside bends. When the connections loosen, it flattens. Geometry, in this sense, is the shape that information takes when it interacts. The curvature of space-time, the gentle arcs that guide planets, and the dramatic folds that birth black holes could be the three-dimensional form of quantum relationships singing together. Translated into the language of metaphor, the cosmos may be a 3D movie projected from a 2D story, written in the language of connection. What we call matter and energy are simply the characters, moving and breathing within that luminous narrative. The more we look at this, the flatter the truth becomes, and somehow more beautiful. For it means that even the deepest mysteries of gravity, time, and light might arise from something profoundly simple: relationships organized into harmony. So, when you gaze into the night and see the Milky Way stretching across the sky, you might imagine that what you see is the universe reading its own story aloud, a story projected from the edges of infinity, retelling itself endlessly in light and motion. And maybe, just maybe, that's what we are too. Living holograms of memory and meaning, flickers of consciousness reflecting a greater pattern. The boundary writes the world, and the world writes us back. Our quiet exploration now turns homeward. After drifting through equations turned to light and geometry turned to music, it's time to return to the scale of the human, to the small, fragile observers who have been peering into this vastness, trying to understand. Because somewhere in this long story about black holes, entanglement, and holograms lies a reflection of us, of consciousness itself. Physicists often say that when we study the universe is, in some sense, studying itself. It's a poetic truth. Every experiment, every telescope, every equation scribbled in chalk is the cosmos turning its gaze inward. The atoms in our eyes are the same atoms that once burned in the hearts of stars. The carbon in our skin was formed in ancient supernovae, and now, billions of years later, those same atoms have become capable of wondering where they came from. We are the universe trying to understand its own story. When Einstein said that his greatest hope was to catch a glimpse of something deeply hidden, he might not have realized how literal that phrase would become. Black holes, once thought to be boundaries of ignorance, have turned into mirrors reflecting the universe's inner logic. They reveal that space and time are not fixed, that information is never lost, that even the deepest darkness is full of connection. And as we uncover those truths, something remarkable happens. The questions we ask about the cosmos begin to sound like the questions we ask about ourselves. Consider the black hole as a mirror. From the outside, it appears simple, silent, featureless, opaque. But within it, according to everything we've learned, lies an infinity of information, encoded on its surface and radiated slowly outward. Doesn't that sound strangely familiar? Each of us too appears simple from the outside, a single being, defined by shape and motion. But within, there are lifetimes of memory, emotion, and thought. Information folded into awareness, sometimes quiet, sometimes radiant. In a way, every mind is its own event horizon, a boundary between the visible and the hidden. When we look at a black hole, we are not just studying gravity. We're seeing a reflection of the same paradox that defines consciousness, the coexistence of interior and exterior, of silence and expression, of the infinite contained within the finite. The black hole speaks to us in the language of the self, a place where everything that falls in is preserved, transformed, and returned as light. It's tempting to think of this as mere metaphor, but perhaps it's something more. Some physicists, like John Wheeler, the man who coined the term black hole, once suggested that the universe might be fundamentally participatory. That observation itself helps shape reality. In his view, we don't merely watch the cosmos, we help it exist by being aware of it. Reality then is not a pre-written play, but a collaboration between the stage and the audience, between being and perception. That notion finds a quiet echo in quantum mechanics. Every measurement, every act of observation, forces a system to choose a definite state from a field of possibilities. Before you look, an electron can be anywhere. Once you look, it is somewhere. In the soft language of philosophy, the universe waits to be seen. The cosmos and consciousness are entangled in ways that may run deeper than we know. You can imagine it like ripples in a vast ocean realizing, for the first time, that they belong to the sea. Each wave believes itself separate, moving on its own path until it senses the pull of the whole, the invisible rhythm connecting every crest and trough. That realization, that we are the universe becoming aware of itself, might be the closest thing to cosmic enlightenment that physics can offer. Black holes help us feel that connection, because they sit at the intersection of opposites. They are regions of ultimate density and perfect emptiness. They hide everything, and yet reveal the fundamental order of reality. In their quiet way, they embody what the human mind struggles to accept, that we can be small and infinite at the same time. When you gaze at an image of a black hole, that ring of fire around a perfect shadow, you're not just looking at a celestial object. You're witnessing the culmination of billions of years of cosmic evolution, the fingerprints of countless particles and fields converging into something that mirrors your own act of perception. It took the universe all that time to make eyes capable of seeing, and now those eyes have turned back to look at their source. The more we learn about the cosmos, the less it feels like a distant alien thing, and the more it feels like an extension of our own nature. The entanglement we see in quantum theory, the unity hidden beneath space and time, the idea that everything arises from connection, these are not only scientific discoveries, they're also quiet affirmations that separateness is an illusion. We are woven from the same fabric as the stars, and the same logic that preserves information in a black hole also preserves every moment of our being. Perhaps that's why so many scientists describe their work in terms of wonder rather than certainty. The more precisely we understand, the more mysterious the universe becomes. The closer we look at reality, the more we realize that it doesn't stand apart from us. There is no outside view, only participation. And maybe this is what it means to truly see the universe, not as a collection of things, but as an unfolding awareness. The cosmos watches itself through our eyes, thinks through our thoughts, and dreams through our curiosity, every discovery is a moment of self-recognition. The universe catching its own reflection and quietly smiling. So as you listen now, somewhere between waking and sleep, imagine this simple truth, that when you look up at the stars, you're seeing yourself, spread across light years, condensed into wonder. The eyes that look and the sky they see are made of the same atoms, obey the same laws and share the same story. You're not separate from the cosmos. You're its way of watching, remembering and dreaming. And when Einstein spoke of a glimpse of something deeply hidden, perhaps he was not just talking about physics. Perhaps he was describing this moment, the quiet realization that to know the universe is, in a way, to know yourself. The path now carries us toward the quiet edges, the places where even knowledge begins to fade into silence. Every field of science, no matter how advanced, eventually meets its horizon, that soft boundary between what can be measured and what can only be imagined. Standing there is not failure. It's the natural rhythm of understanding, the point where curiosity exhales and mystery takes a slow, patient breath. In many ways, black holes taught us how to stand at this edge. They show us that boundaries aren't walls, they're invitations. The event horizon, that invisible line where gravity holds even light, is not the end of physics, but the beginning of wonder. It marks the limit of what can be seen, and yet, it's precisely there that the universe whispers its deepest secrets. Science, too, has its horizons. The equations that describe space-time bend beautifully until they reach the singularity, where they shatter into infinities. Quantum theory predicts probabilities with exquisite precision, but it cannot explain why the world feels definite. Even our understanding of consciousness, the very awareness that allows us to ponder these questions, remains elusive. We can trace brain activity, map neural patterns, even simulate cognition, but we cannot yet locate the spark that turns matter into mind. There's a humility that comes with admitting this. Every discovery opens not a door, but a hallway of new questions. Each answer becomes a window onto deeper ignorance. The closer we get to truth, the more delicate it becomes, like starlight scattered across glass. And yet, there's beauty in that incompleteness. If the universe had no mysteries left, it would lose its poetry. It would stop inviting us to dream. Physicist Richard Feynman once said that he could live with doubt, uncertainty, and not knowing, and still find the world beautiful. Perhaps that's what it means to dwell at the edge of knowing, to find peace in wonder itself. You don't have to solve every equation to appreciate its symmetry. You don't have to map the entire ocean to love its sound. Some mysteries are not meant to be conquered. They are meant to be kept as gentle reminders that curiosity is its own form of grace. The more we learn about the universe, the clearer it becomes that reality is not a single truth but a living spectrum. There are regions of clarity where things can be known precisely, the orbit of a planet, the charge of an electron. And there are regions where clarity fades, where time stretches, where light curves, where even cause and effect blur into one another. These edges aren't mistakes in the design, they're features. They keep us moving, asking, imagining. Einstein himself often spoke about this. Toward the end of his life, he confessed that he still felt like a child picking up pebbles on the shore of a vast unexplored sea. Coming from the man who had redefined our understanding of space and time, that confession wasn't modesty, it was reverence. It was the recognition that the unknown is not an enemy of knowledge, but its source. Without darkness, light has no meaning. Without mystery, truth has no direction. Perhaps that's why black holes fascinate us so much. They sit at the edge of knowing, not just scientifically, but emotionally. They embody the tension between understanding and surrender. You can calculate their mass, model their radiation, even simulate their mergers on supercomputers. But the moment you reach the horizon, mathematics falls silent. Beyond that, only imagination can travel. In that sense, studying black holes is like studying the human heart. We can measure the beats, chart the rhythms, even model how it circulates life. But we can't write an equation for love or longing or the quiet ache of beauty. Those are the horizons of the inner world, edges that we learn to respect rather than explain. There's a line from the physicist Niels Bohr that says, "The opposite of a profound truth may well be another profound truth." It's a way of reminding us that the world doesn't always fit neatly into binaries of right and wrong, light and dark, known and unknown. At the edges, opposites blur and contradictions coexist. Time and space exchange roles near a black hole. Light behaves both as wave and particle. The universe seems to delight in paradox, as if to remind us that reality is larger than logic alone can hold. To live with that realization is to practice a kind of scientific mindfulness, to let the unknown exist without anxiety. It doesn't mean giving up on discovery. It means understanding that discovery is endless and that every answer eventually curves back into question. Just as a photon bends around a black hole, knowledge too bends, circling mystery forever. When we reach these limits, it helps to listen rather than measure. Silence can be its own form of observation. There are edges even light cannot cross, but their presence still shapes the stars. Likewise, there are questions we may never answer, but their existence still illuminates the human spirit. And maybe that's the greatest lesson the cosmos offers, that we're not here to conquer the universe, but to be part of its unfolding, to listen, to marvel, to participate. The unknown is not a gap to fill, but a field to wander. So tonight, if you find yourself wondering where knowledge ends and mystery begins, think of a horizon, not as a line you can't cross, but as a place where sky and sea meet, where light becomes colour and colour becomes night. Beyond it, there are still stars, still stories, still infinite questions waiting quietly for their turn to be discovered. Not every mystery must be solved, some must simply be heard. And maybe that's enough. To stand here, aware, at the edge of knowing, to look into the dark and feel the gentle hum of curiosity, is already to be part of the universe's ongoing conversation. Our quiet journey now drifts toward connection, not as a theory or a formula, but as the simple, living truth that binds all things. For after all the equations have been softened into meaning, after the mathematics has been translated into breath and light, what remains is a single idea that hums beneath the surface of everything. Nothing in this universe exists alone. Every atom in your body was once part of a star that burned billions of years ago. Every breath you take carries oxygen once breathed by forests and oceans, and perhaps by other beings long vanished into history. The same cosmic particles that pulse inside the sun move through you now. Even the photons of light that strike your eyes tonight began their journey in the hearts of galaxies, crossing unimaginable distances just to arrive in this quiet moment. Science calls this continuity. Poets call it belonging. The universe, it seems, is not a collection of isolated things, but a single unfolding conversation, each part responding to the others in patterns too intricate to see. The black holes we've explored, the galaxies that spiral in silence, even the space between them, all of it is a single fabric, woven by interaction. And if the universe is a fabric, then perhaps we are threads within it, not spectators, but participants. Every movement, every thought, every act of kindness is a small vibration along that web. It's easy to forget this in daily life, when our worry seems small and separate. But physics reminds us that separateness is only an illusion. The same laws that entangle particles across light years connect our own hearts in subtler ways. Quantum entanglement, when softened into human language, tells us that relationship is more fundamental than location. Two particles that share a common history remain linked, no matter how far apart they drift. If we stretch that idea beyond physics, gently, metaphorically, it becomes something quietly profound. That connection, once made, endures. When you share a moment of empathy, when you listen deeply or comfort another, you're adding your own thread to that cosmic weave. Maybe that's what gravity really is. Not just a force that pulls masses together, but the natural tendency of the universe to stay connected, to remember itself. And the Earth doesn't fall toward the Sun because of command. It falls because of relationship, because space itself curves in response to the presence of others. If we translate Einstein's elegant equations into feeling, they whisper this, that to exist is to respond, and to respond is to belong. You might even think of gravity as the softest language of love, the quiet insistence of matter that says, we're not apart. And if that's true, then all of existence becomes an act of communication. The cosmos doesn't just expand, it speaks. Galaxies collide and merge like ideas forming, sentences. Black holes sing their low, patient songs of space-time. Light crosses the void, carrying messages older than any civilization. And we, for our part, listen, building telescopes, writing equations and telling stories that help the universe hear itself more clearly. There's a certain symmetry in that. The same pattern that appears in the physics of connection also appears in the poetry of experience. The universe entangles particles, we entangle lives. It weaves space-time, we weave meaning. Every conversation, every shared silence becomes a small reflection of the larger structure, a microcosm of cosmic empathy. Sometimes I like to imagine that if we could translate all those interactions, between particles, between people, into sound, the universe would be full of gentle harmony. Not a perfect one, but something like music nonetheless. Dissonant in places, resolving elsewhere. Each star a note, each life a variation on the same theme, the longing to connect. You could call it the dream that connects everything, the dream the universe has been having since the moment it began. It dreamt of light and darkness, of gravity and form, of life emerging from the dust of stars. It dreamt of awareness, eyes that could look back at itself, minds that could ask why. And within that dream you appear, a spark of consciousness held delicately in the web of time. Perhaps the deepest revelation of science is not that the universe is vast, but that it is continuous, that no boundary is absolute. Even time, which we often think of as linear, flows like a river branching into countless streams, some converging, some diverging, all part of one greater current. Every ending, somewhere, becomes a beginning. Every silence hides the vibration of something still singing, and so we learn to see ourselves differently, not as small observers trapped in a large cosmos, but as living expressions of its unity. The carbon in your cells, the rhythm of your heartbeat, the curve of your thoughts, all of it is the universe performing itself in miniature. You're a tiny echo of its pattern, a brief resonance of its infinite complexity. It's a comforting thought, isn't it? That even in loneliness, you're never truly alone. The night sky isn't above you, it's within you. The same equations that describe the collapse of stars also describe the dance of your neurons. The same symmetry that shapes galaxies guides your breath. When you smile, somewhere, perhaps imperceptibly, the cosmos smiles back. Physicist Brian Greene once said that we are the universe made conscious. In softer words, we are the dreamer realizing it is dreaming. Every time we learn, create or love, the universe awakens a little more to itself. Maybe that's why connection feels so sacred. Because it's not just emotional, it's structural. It's how reality holds itself together. And if all this seems grand, remember that the grandeur hides in the smallest things. The way sunlight glows through a leaf, the hush before dawn, the simple warmth of another person's hand. each as a thread in the same cosmic web, binding galaxies and moments alike. Perhaps, then, our purpose is not to solve the universe, but to keep participating in its unfolding, to be present, aware, and kind, to let curiosity lead us without the need for final answers. We might all be quantumly entangled over morning coffee, connected not by equations, but by the quiet rhythm of shared existence. And maybe that's enough, because when the universe looks through your eyes and feels through your heart, what it sees, what it feels, is itself, alive, curious, and beautifully incomplete. And so, we've reached the quiet edge of our journey, the place where all roads in science and wonder seem to meet, then dissolve softly into silence. We began with darkness, with the quiet gravity of black holes, and the question of whether the universe could ever forget. But as we've drifted deeper, we've found that even the darkest places shine with memory, that every silence hums with connection, and that every ending hides the shape of a beginning. Tonight, as we stand at the final horizon of our story, the universe feels both vast and intimate. All that complexity, the curving of space-time, the trembling of quantum fields, the echo of ancient stars, gathers quietly here in this one still moment. It's a moment that belongs not just to science, but to reflection, to the human act of looking up and wondering. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. Perhaps what he meant is that the cosmos is not something we stand apart from, trying to decode like an alien language. It is something we are made of, something that speaks through us. When you understand even a small part of it, when you grasp how light bends or how gravity shapes time, you're not merely learning about the universe. You're remembering what you already are. Maybe that's why black holes, strange and remote as they seem, have such a powerful pull on our imagination. They are not just physical mysteries. They are mirrors that show us our longing to understand, our fear of the unknown, our faith that knowledge can outshine darkness. In a way, every scientific question is a kind of prayer, a reaching toward the hidden order of things, trusting that the universe will answer in its own time. We've seen how black holes bend light and time, how they store information on their surfaces, and how even they are not eternal. We've followed the thread through quantum entanglement, through wormholes and holograms, through the shimmering boundary where space and time themselves begin to emerge. And at the end of it all, we've come to something profoundly simple. The realization that everything is connected, that nothing is lost, and that existence itself is an act of remembering. The universe, it seems, never forgets. Not the birth of stars, not the fall of matter into black holes, not even the brief spark of consciousness that asks these questions. Every event, every vibration, every thought leaves its mark on the cosmic fabric, woven into a tapestry that stretches beyond what we can see. The pattern is vast, but it's not cold. It's full of meaning, full of memory. Perhaps then, to glimpse what is deeply hidden is not to uncover a secret equation or a final theory, but to recognize that the mystery itself is alive, that the search is part of the design. The horizon doesn't end the story, it keeps it unfolding. Like the event horizon of a black hole, knowledge curves toward the unknown, forever drawing us closer, forever reminding us that curiosity is the universe's way of staying awake. There's a quiet comfort in that. It means that uncertainty is not a flaw, but a feature. The unknown is not a void, but a promise. It is the reason there is something rather than nothing, the space in which discovery can happen and wonder can grow. When we first imagined falling into a black hole, it seemed like falling into an end. Now it feels more like falling into an origin, a place where everything is gathered, compressed, and ready to become new again. What we once called singularity might be the seed of another beginning, Another universe waiting patiently in the folds of this one. The end of time might simply be time learning to turn itself inside out, and maybe that's what we've been doing all along, turning inside out. Each discovery, each act of awareness, each spark of creativity, it's the universe folding back on itself, revealing another layer of its design. When you close your eyes and imagine the cosmos, you're not looking away from it. You're looking deeper into it. You're one of its thoughts, momentarily self-aware, dreaming about where it all began. Somewhere out there, a black hole still hums softly. Its event horizon glows with the faint warmth of Hawking radiation. Its surface holds the memory of everything that has ever fallen in, every photon, every atom, every whisper of light. And though it may take longer than the lifetime of galaxies, one day all that stored information will return to the universe scattered again as light. Even in darkness there is generosity. So tonight, if your eyes are open, look up. The stars you see are already gone, and yet their light still travels. Proof that memory transcends distance and time. And if your eyes are closed, imagine that same light flowing through you, because it is. You are made of it. You are a continuation of that story, a soft echo of the first light that ever was. And perhaps this quiet recognition, is what Einstein meant by a glimpse of something deeply hidden. Not a secret buried in equations, but the awareness that the cosmos and consciousness are one continuous act of unfolding. That when you feel awe or love or peace, you're aligning with the same order that keeps the planets moving, the same geometry that shapes the stars. We began with darkness and found light. We sought an end and found a beginning. We followed gravity into silence and found the voice of the universe itself, speaking softly through connection, through curiosity, through you. So rest now, traveller. You've journeyed across horizons, through time and thought, through the deep waters of existence. The stars are still listening. The black holes still breathe their patient warmth. And somewhere, in the great quiet of the cosmos, the story continues. Not in equations or telescopes, but in the small, steady rhythm of your own heart, still beating in time with the universe. Maybe the universe never forgets, and neither do we.